Hello, everyone, and welcome back to the wide world of Organic Chemistry Lab. Today, we will be looking at CH4521, that's Organic 2 Lab, specifically the Wittig reaction, preparation of steel beam. This is a 2-week experiment, and so we're going to be seeing both weeks in one video, and there will be a flag or banner like what you're seeing right now that will tell you when this happens. All right, so as we watch, glassware is being prepared. We have a round bottom flask with what appears to already have a magnetic stir bar in it in our metal plate, which we can use as a heating mantle when the time comes. Now, what we need to recognize here is this is the first week, so the whole point is that we're trying to take our phosphonium salt and produce the Illid from it. So we're going to start with our 2.51 grams of benzyl triphenylphosphonium chloride. All right, and they already had the DCM in the round bottom, so they're just pointed out so that you can see the quantity that they're about to measure out, the volume, and they're going to need 7 milliliters of that. All right, so they're just adding it back to the 25 mil round bottom. Now they're going to add our phosphonium chloride with all that other jazzy stuff attached to it. All right. All right, and then what we're going to see is they're going to go ahead and set up for a reflux. Oh, wait, sorry, I forgot. We got to do the benzaldehyde. All right, so they're going to do 0.7 milliliters of benzaldehyde. I mean, as you can see here, I've asked the question, what is that based on the density? And so using volume, it's going to be we're going to have to convert that to a mass and then a moles, right? Because the whole point at the end is that you are going to have to come up with the theoretical yields and the percent yield based off the product mass. All right, so here they have set up for reflux. They've added their benzaldehyde, their phosphonium chloride, and their DCM. All right, and it looks like it is already stirring, but they haven't started heating yet because they haven't actually hooked their water hoses up to the condenser as they're doing now. Whoa, be careful, it popped out of the well. Okay, there we go. All right, we have water. Welcome to the water. All right, we're gonna crank up them RPMs. All right, how much horsepower does your hot plate have? All right, and then we're heating supposedly gently. Yeah, 50 degrees C. That's not too bad. So gently heating. Well, now it's jumped down to 42. Is there something wrong with this hot plate to where it can't make up its mind? All right, so anyway, gentle heat, so we're going to need it to reflux. It's kind of fun to watch that water trickle down that hose. It's like rhythmic. Oh, we didn't like how that was heating. So you know what we say? More power. Ooh, more power again. All right. So now it's reflux for a while. We're adding our sodium hydroxide solution. We're going to need to add that dropwise. I wonder why we're adding sodium hydroxide. Right? If you pay attention to the first step of this reaction where we create our Illid, that will be our Wittig reactant. You'll notice in the product side, you have protonated base and BR. Oh, sorry, we're adding our base, sodium hydroxide. We're adding our base. All right, so we haven't produced the Illid yet, but with this dropwise addition, we're adding base to produce that Illid. So we should have, as the description or as the molecular structure shows in the lab manual, we're creating a negative charge on that carbon that's directly bound to our phosphorus atom in the phosphonium chloride, making it a reactive species. Now, also pay attention to this solution color as we add our base, our sodium hydroxide. I mean, it's not going to happen right now, but pay attention. And don't look at that super rhythmic like design of water trickling down that hose. We have our own water feature in this video. Totally feng shui. Oh, there it goes. See it? Nope, because you were looking at the water feature. Pay attention to the round bottom flask. Mmm, that looks like a color change. Mmm. Or is it? All right, and they've just added the lab. Whoa, okay, yeah, that. That was a color change. You see that? Yep. That's real pretty. I like that color. Well, I don't know. It kind of looks like snot. Oh, here we go. All right. So they have, after this reaction with our sodium hydroxide, they're now allowing it to cool to room temperature. And the snot color's gone. Well, I don't know. It still kind of looks like snot. It just looks like someone doesn't have the flu. All right. So while it's cooling, they're letting it stir still. All right. Now they're setting up for a separatory funnel, and what we're going to see is them using the reaction mixture that's in that round bottom flask right now. It's stirring. Right? I mean, why else is it shaking? Because if there's an earthquake going on, they shouldn't be in the lab. Okay. We're just waiting because we're patient. hmm We are. Oh, there it goes. Okay. So they added that reaction mixture to the separatory funnel. And now we're going to add 5 mils of DCM rinse. Well, technically they have 10 because they're doing the rinse twice. So they're just trying to get everything out of that round bottom flask. All right. All right. All right. There we go. Cool. All right. Let's zoom in on that separatory funnel. Let's zoom in a little more. Ooh, ooh, zoom in, zoom out. What y'all got there? I'm going to assume this is more DCM because we haven't tried to do our first separation yet. So, which layer is the DCM? If you pay close attention, they show you. All right. So we did a little shaky shake. And you can visibly see two layers now. All right. Ooh, 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 ooh. There we go. All right. Bottom layer is in its own Erlenmeyer. That's called an Erlenmeyer flask. Now our top layer is in an Erlenmeyer flask. Here are our two layers. Bottom's on the left. This is the part where you pay attention. Oh, that's a marker. Huh. Huh. That says organic layer and aqueous layer. So you want to keep the organic layer and make sure you put that Sharpie up. You don't want to get writing all over you. All right, yes, point and add. There you go. All right, so we've got our organic layer in the separatory funnel, and there's a bottle that says bisulfite. I bet it's sodium bisulfite. It is. All right, so they're adding the saturated sodium bisulfite. Fun fact, sodium bisulfite is slightly acidic, so I wonder why we're adding it. The reaction used a base. I don't know why that's important. But anyway, they're adding more sodium bisulfite. All right. Watch this. Shaky shake, shaky shake, shaky shake, shaky shake. Vent. Shh. Do we shake? Okay, we're done. We vented the once. That's good. All right. All right. So we are looking at the two layers yet again. So sodium bisulfite, that would have been in water. So that would have been our aqueous layer. And yet again, our solvent was DCM. So DCM having a higher density, it was our bottom layer, which has our Illid in it. All right, now the bottom layer was tested for pH. It came up neutral, so that's why now you see us skipping ahead to adding this powder, and this powder is our drying agent, sodium sulfate. All right, and we add more. All right, the way you can tell usually when you need to stop adding drying agent is when you can see like slight flurries. So that kind of looks like a gel because it's still soaking up water. Or still, I guess the technical term would be absorbing, but it's still sucking up water. So you just keep adding a little bit until you can see some flurries left over. And that means you've absorbed all the water. All right, so it's being allowed to just sit there and kind of dry, like absorb the water. All right. And then what we're going to see next, they're going to transfer this to a screw cap vial, screw top vial. And they're going to store a little bit of that drying agent in there. But we won't have to wait a week for another video. The beauty of the camera. All right, so transferring our Illid solution and some of that sodium sulfate clumpiness. He do the clumpy clump. He do the clumpy clump. All right, and so this is what it would look like at the end of week 1. Now, we shall begin week 2. We're transferring that Illid solution to a test tube. Boom, boom. Right, now we're bringing in some fresh DCM, dichloromethane, fresh off the presses. Then we have 75 milligrams of I2. Shake it, don't break it. All right, here we go. All right, so they shook it up some, and what we're going to do now is we're going to irradiate. That is such a fun word to say. We're going to irradiate for 1 hour. So make sure you watch closely over the course of the next hour, because crazy things are going to happen. Yes, this is how we irradiate. Whew, the hour flew by. Here we go. Next, we're going to transfer that to here it comes. Here it comes. There you go. We're going to transfer that to the separatory funnel, and then we are going to wash that with some saturated aqueous sodium bisulfite. So we're adding a little bit. There we go. Yeah. So about 5 milliliters of that saturated sodium bisulfite. All right. Now the whole point of this, so the sodium bisulfite will react with the I2, and it will create iodide and other iodide-related ions. But you'll notice like a slight color change here, where it's goes from like a deep brownish-looking color to like an iridescent yellowish green. Yeah. Yeah, baby. That's it right there. All right, so we have 2 layers. We have our aqueous, and we have... Wait, what are they adding now? I couldn't see the bottle, so I'm assuming that's more sodium bisulfite. Ooh, she's shaking that. Look at that. Whoa, that thing. You don't want to put your hand in the way of that separatory funnel. Because we're safe. We practice safety in the lab, people. Get it right. All right, so 2 layers yet again. DCM with that sodium bisulfite. So where's our stuff? Where's the product we're looking? Oh, it bubbled because you got to take the top off. Yep. All right, 2 layers yet again. Tag team back again. Now we're going to stare at the separatory funnel for a second. All right, so we re-add our snotty stuff. Now we're going to wash our dichloromethane with saturated sodium chloride, also known as a brine solution. You'll hear that a lot too. Watch, shake. Whoa, man, that's some vigorous shaking. That is some good separatory funnel mixing, shaking stuff. All right, that's how you get it done. All right. You can see the 2 layers, right? Because it's aqueous sodium chloride. All right, so we washed it up. All right, our bottom layer, yet again, should be the organic layer, because DCM, yeah, it's got a density. It's more dense. I said dense, people, not dunce. All right, and so now what we're going to see, we're going to need to dry our organic layer. So they're adding it again, sodium sulfate. It's sitting there. Oh, okay, we pick it up because it felt lonely. Anyway, so just shaking vigorously so that we can maximize how much of the water that's remaining gets absorbed. All right, so now they're transferring the dried solution to a rotovap round bottom flask, and they're going to add a little more DCM to maybe try and get any trapped producto. All right, the rotovap's doing its thing. All right, so you can sort of see, not the big bulb, but right below that green thing you see spinning in the tank in the round bottom water bath. All right, so they're just distilling off the DCM. Ooh, that thing's spinning. All right, so they were able to distill off all the DCM. So now what they have on the hot plate, that's ethanol, hot ethanol, and they're going to, well, I guess you see them doing it. They're putting it in the round bottom flask that had our solid. We should have not a cysteine, a steel beam. All right. Now it's gonna dissolve and stuff because it's hot, right? Since it's hot, so you've increased the solubility, right? And for the most part, it's okay if it doesn't all dissolve because either way, um, well, I guess you would prefer it to. That way, any trapped DCM could not get trapped in the crystal structure. But all right, so now they are using an ice water bath in order to crystallize. Oh, they did that fast. All right, and so now it's sat for the desired 15 minutes. Well, it doesn't say, but it's sat there long enough that we saw the precipitate fall out of solution. So now they're setting up a Buchner funnel and with a Buchner flask. All right, and they hooked it up to a vacuum so it'll suck everything out. So they're using some of that ethanol to wet the filter paper so it'll stick. Now they add. All right, and then they're going to add some cool ethanol. All right, try and rinse everything out of that rotovap round bottom flask. All right, and then if you apply some gentle pressure, you will be able to hopefully get all the ethanol sucked down at the bottom. Drip, 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 until your brain go pop. Uh-huh. Yeah, I see that filter paper. Look at that filter paper. All right, they're done. So they disconnected the hose. And so now they're going to try and dry their filtered paper with on a watch glass. All right, and there are solids trapped on that filter paper. All right, now one note of caution. It looks like that temperature was like 157 degrees C. That's going to burn that paper. So you either want to watch it or you want to kind of drop the temperature down so that you don't burn the paper. Because if you burn the paper, then your mass isn't going to be correct. So when you try to get the mass of your final product. All right, so now weighing the filter paper, watch glass, and product, you get 27.2095 grams. Now, to get the actual mass of your product, you are going to have to subtract the mass of the filter paper and the watch glass. That mass is going to be given as a separate link with the Wittig experimental details in Canvas. So do look for that so that you can do that subtraction properly. And then it's not actually shown. I think there were technical difficulties with the camera battery or something, but it melted. But you're not going to actually get to see it melt before the camera shuts off. But the melting point range was recorded to be approximately between 119 and 124 degrees C. All right, so hang on, here it comes. Bloop. See, I wasn't lying. Between 119 and 124 degrees C. All right, I know I don't have my degree symbol. Do not critique me on that. It is not easy to do a superscript in this program. All right, adios. Bye bye. See you later. Okay. How do I stop?